For a long time, scientists debated about the dual nature of light and thought it could be either a wave or a particle. Now we know that radio waves and visible light and X-rays and gamma rays are all photonic packets, and they are all part of what we call the electromagnetic spectrum. But gamma ray photons contain the highest amount of energy. As shown by the red and blue model graphic, photons are complex in that they exhibit both electrostatic E fields and magnetic B fields at the same time. The paradox is that we've seen this requires both stationary and moving electrons to exist at the same time within the same photon. To add to the complexity, we can see that these fields are not out of sync. The photon model in this first slide shows that they both occur at the same time with matching peaks, otherwise known as in-phase peaks. Other sources sometimes model photons as oscillating electron currents that produce E fields. However, as we have seen, oscillating electrons would lose energy and therefore cannot sustain this type of model. However, the gummy triad models make photons understandable without such losses, while consisting solely of up quarks and quark electrons. In this next slide, we start with our knowledge of the gummy models from Part 1. We know that a down quark can change into an up quark and a quark electron. From Part 2, we use our knowledge that an electron can always turn into a photon and another electron, as for example when an orbital electron drops down to a lower energy shell. From Part 3, we use our knowledge that quark electrons are transforming and hopping around an up quark without losing energy. Now in this slide, one can pause the video and derive that an electron has the option of turning into an anti-up quark and a down quark instead of turning into a photon and another electron. Finally, we use an accepted theory of stellar fusion from Part 4. Energy sources can generate electron-positron pairs from nothing, and then photons can be generated by those electrons. When we add one of these electron-positron pairs as an option, we see that the four particles can be grouped as a neutrally charged entity that will be our model for a photon. And there is an unaccounted for electron left over, but that is just our original electron turning into a photon and another electron. In this next slide, we show a generalized model of how a stack of the four particles in one dimension can produce an E field. And a moment later, when a hop and a flip occurs, they can produce a B field simultaneously, with no loss of energy. Of course, models at this quark level can't be verified, but we can generalize such a model from the principles already listed, and as such, this model is intended to be an aid to understanding the complexity of photons. Note that the letter E represents quark electrons, and the letter U represents up quarks, and the Greek symbol lambda represents the photon or photon stack. We next generalize that this is a non-collapsing stack due to the offsetting attractions and repulsions among the particles of different charge magnitudes, as was the case for non-collapse in the gummy proton model in Part 1. The electron at the top of the photon stack does not collapse to the center of the stack. Instead, as explained in Part 1 continued, the electron undergoes the equivalent of tidal force and is transformed into neutrality so that it can hop to the other end of the stack and swap positions with its positron mirror image. In the case of this photon stack, the up quark and anti-up quark hop and swap at the same time. Also, as shown in the slide, the E field cycles through flips of 180 degrees, which appears to the outside world as an electron rotating. This observed electron rotation is what produces magnetic B fields that are alternately pointing in and out of the page. Note that this model explains why the E field and the B field are in phase and are at right angles to each other and at right angles to the direction of propagation. This next slide reminds us that electrons can carry off different amounts of energy. For example, an orbital electron in the lowest energy shell of an atom will jump to higher and higher energy shells as it gains more energy. But photon and electron stacks have no shells to jump to, so they just flip faster if they have more energy. A blue photon has more energy than a red photon, so its stack will flip faster. And this is observed as blue light having a shorter wavelength, or a higher frequency, than red light. When a blue photon stack flips faster, the photon electron travels a shorter distance downrange between flips. So the downrange velocity of all photons becomes a constant, namely the speed of light, c. Again, this is because a shortened jump distance is exactly offset by a shortened jump time, and therefore the velocity is independent of wavelength or frequency. Now in this slide, the graphics show how amplitude-modulated signals are embedded in the photon packets. When we modulate a red laser beam amplitude with a signal, what we are really doing is increasing or decreasing the number of photons in the packet at that time. In the example shown, the number varies between 1 photon and 3 photons. So the E-field strength is just the sum of the photon E-fields at a given point in time. More photons means more E-field strength. This same principle also applies at radio frequencies. Driving energy into an antenna causes electrons to leave the metal as RF wavelength photon packets. And a modulating current of antenna electrons means that the number of photons being produced will vary with time. This next slide reminds us that any photon model must answer the question of how can we observe both a stationary electron and a moving electron at the same time. And we saw how the gummy photon model does this, by having a momentarily stationary electron do a lossless flip of its E-field stack, while generating an in-sync B-field at the same time. At longer RF wavelengths, the energies are so low that the requisite photons can be generated with external antennas. If we jiggle an electron in an antenna so that it produces just one photon, then when that photon strikes a receiving antenna as shown, it will jiggle the antenna electron at the same jiggle frequency. If the antenna is part of an inductor plus capacitor circuit loop, a resonance will be observable and the RF modulation can be decoded electronically. Note that both the E-field and the B-field will jiggle the receiving antenna electron in the correct orientation to maintain an E-field alignment with the source. In this last slide, the photon has its E-field lined up in only one plane, and this is known as linear polarization. This slide explains the classic process of reducing glare off of a car hood with polarizing glasses. Recall that the speed of light in a vacuum is reduced when traveling through a medium. But how? Well, for visible light photons, it is only the index of refraction in the plane of the E-field that actually reduces velocity. This also becomes important to know for any future discussion on circularly polarized light involving anisotropic media, which is media that has different indices of refraction in different axes. We know that photon electrons are slowed down when they interact with the other electrons in the atoms of the medium being traveled through. This can be an E-field or B-field interaction. Fast-flipping blue photon stacks interact more, and therefore are slowed more than red photons, for example. Even if the photons are not absorbed by the new medium, a well of nuclear attraction slows them down. Recall that orbital electrons are bound to the nucleus by virtual photons, forming a sort of nuclear attraction well for electrons. Also know that the stack flipping rate doesn't change, so the colors stay the same when we wear goggles underwater, but the photons are definitely dragged down to a speed slower than c. And when the photons leave the medium and there is no longer any interaction with these wells to slow them down, then the photon velocity returns to c. From the first two bullet points, we see that polarizers are just grids of conductive antennas made from molecules or wires. Note that blocking occurs because photon electrons are absorbed by electron E-field interaction. So for the polarizer to block the horizontal glare E-field, the antenna must be parallel or horizontal with the car hood. Circular polarization can be generated from wave plates that have different indices of refraction in different crystalline axes. If we have wave plates that are quarter wave and another one that's 3/4 wave thick, then the opposite direction circular polarizations are generated. And those two wave plates are what you're wearing when you use polarized glasses at a 3D movie theater. But those details are an interesting topic for another day.